Okay, this is sort of an extra flipped lesson. I didn't originally have this one up, but we more covered this with the practicals that a lot of people have done around the precipitation reactions and solubility. But the other thing I'm going to use this flip lesson for is to just review the process of writing and balancing chemical equations. This is something that I must admit I normally focus on a lot with my Year 10 students. But I know not everyone, some of you in Year 10 have done a lot of this, so you'll probably find this pretty straightforward, but not everyone's done a lot of this stuff in Year 10. So I thought it was worth doing another flip lesson, just going through the precipitation reactions and writing and balancing chemical equations, because precipitation reactions is an excellent vehicle to use to look at that stuff and test that stuff. Let's get into it. Okay, so what's our learning intention? What's our success criteria here? Particularly, I think we'll focus on our success criteria, write ionic equations for precipitation reactions. So there's a few things going on here, and we're going to get to the ionic equations, but there's a number of steps we need to understand before we get there. So the first is, what is a precipitation reaction? So in a precipitation reaction, two dissolved or aqueous ionic compounds react to form an insoluble solid precipitate. They achieve this by swapping partners, as shown in the diagram. So if we take one ionic compound that's dissolved, and we've just used the A and the X, and the A, in this case, usually means a positively charged, which is usually a metal ion. So it would be something like a sodium ion, or a calcium ion, or something, some other metal ion. And then X and Y are usually negatively charged ions. So that's a negatively charged ions. So they're usually non-metals, so they could be things like chloride. But they could also be things like polyatomic ions, like, say, the sulfate ion, for example. It's just a couple of possible examples. So we would take two of these ionic compounds, both of which are dissolved in water, so they're solutions, they're dissolved. And when we react them together, and hopefully you've done this in the lab, or if you haven't done it in the lab, you will do it in the lab, often you'll see that one thing will form a precipitate. So by a precipitate, we means it forms something that's solid. So it's something that is insoluble, it's something that is solid. We show that in the equation with a little s for solid. The AQ means something is soluble or it's dissolved in water. Liquid and gas are also other subscripts we use in these equations, but they don't really apply in precipitation reactions. So when we react these two things together, generally A and X are together and B and Y, but when we react them, the A and Y are able to get together because they're both, I talked about them being hydrated, they're both hydrated, so they're pulled apart from the lattice and they're just held in water, held in solution surrounded by the water molecules, the polar water molecules. I talked about that in the last flip lesson. And then the same things happens with the B and the X here. So they basically swap over so we can form AY and BX. And if one of these things is insoluble, and I'll show you how we work that out in the next slide, then it will form a precipitate. So an example of what that might look like, if we took copper sulfate, you've probably used that in the lab sometime, that's a blue solution. We reacted it with sodium hydroxide, often caustic soda, or it's what's used in drain cleaner and lots of things. Quite possibly have used that in the lab. That will form copper hydroxide because the copper gets together with the hydroxide. That will actually form the solid. We'll explain why in the next slide. And the sodium and the sulfate can get together, but in that case, they won't form a precipitate, a solid precipitate. They will remain dissolved or aqueous. So that's what they will form there. So that basically shows that process of what happens in a precipitation reaction. We'll explore more how we write equations for those and then ionic equations and how we work all that out in the next slide. Okay, so we have our solubility rules here. They are what is going to let us work out whether things are going to form soluble compounds, which will be aqueous, will dissolve in water, or insoluble compounds, which will not be soluble. They will not dissolve in water. They will form a solid. And these rules basically say that nitrates, this is one of our polyatomic ions, are all soluble. Chlorides and iodides are all soluble except for Ag+, which is silver, Hg+, which is mercury, and Pb, which is lead. With the sulfates, another one of our polyatomic ions, 1 sulfur, 4 oxygens with a 2- charge. They will be all soluble except for Ba, barium, Sr, strontium, and Pb, lead. And carbonates, another one of our polyatomic ions, CO3 2-, they will be all insoluble, so they will all form a solid precipitate except Na, sodium, K, potassium, and NH4, ammonium. This is a positively charged polyatomic ion that we often see. Hydroxides, another small polyatomic ion, they will be all insoluble except, same exceptions as before, sodium, potassium, and ammonium. So let's have a look at how we work out what happens in these reactions, these precipitation reactions. And we'll start by doing a word equation, which is often where I would start, particularly say with a Year 10 class. So we've got this reaction where we've taken some copper sulfate solution, a blue solution, and we've reacted it with sodium hydroxide, a standard base that we would use in the lab. And we want to show that reaction. We would write that out as, sorry, just screen's jumping around a bit here. My lights are going off. Copper sulfate. And to show it's reacting with something else, we would use the plus sign. Is reacted with sodium hydroxide, so that's coming from the question. And then they will go to form, they do their partner swap, so we end up with copper hydroxide plus sodium sulfate. So hopefully you can see there that we've gone with the copper has joined up with the hydroxide and the sodium has joined up with the sulfate. That's our sort of little partner swap. Now, that's a word equation. We now need to turn that into a chemical equation or a chemical symbol equation. And to do that, we start out, well, copper. Now we're doing, everything here is ionic substances, metals and non-metals joined together. So we're dealing with ions. So we've got copper. What's the symbol for copper? We can look at our periodic table and we can see that's Cu. How do we know the charge on copper? As you do these more, you will remember these. But this year, I will always give you a cheat sheet. It was attached to the last page of the practical that we did in class. Will tell you that copper forms a 2+ ion. And sulfate, it's one of our polyatomic ions, SO4, forms a 2- ion. That's up here in the chart as well. Now, we've got a 2+ and a 2-, so they balance each other out. We don't need to do anything more there. If you remember when we worked out ionic formulas, when we did ionic bonding. Then we've got sodium hydroxide. Sodium from the periodic table is Na. It's in group 1. It loses 1 electron, so it forms a 1+ charge. But again, that's on your cheat sheet for this year. And the hydroxide ion, polyatomic ion with a 1- charge, that was up here. 1+, 1- balance out, so we don't need to change anything else there. And then they go to form copper, still a 2+, hydroxide, still a minus, but a 2+ and a 1- don't balance out. If you're a 2+, you need to have 2 minuses to hang out with. So we need 2 hydroxides. So because it's a polyatomic ion, we put the brackets around it. So we would have 2 negatively charged hydroxide ions, giving 2- charge in overall, and a copper ion which has a 2+, 2+ and 2- now balance, plus we would have sodium, Na+, plus, and then sulfate, our polyatomic ion again, SO4, 2-. Again here now, a plus and a 2- don't balance out. That's no good. We need 2 pluses to balance out the 2-, so we need 2 sodiums. So we put a little 2 down there. So when we're working out the formula of these things, we put in the little numbers at the bottom. 2, 2, didn't need to put in the on the other side. Let's have a look at another one. Lead chloride is reacted with silver nitrate. If you wanted to pause the video now and have a go at writing out the word equation, that'd be good on a bit of paper. But I know no one ever does that when you say pause the video, but just in case, there's your opportunity. There, let's do it. So lead, look at our periodic, so let's do a word equation first. Lead chloride, so it's reacting, so we put a plus sign. Silver nitrate, and they're going to do their swapsies. So we're going to end up with lead nitrate and silver chloride. Don't need to draw those arrows in, I'm just trying to highlight that for you guys. So what did I just say? Lead nitrate plus silver chloride So there we have done our word equation. Now, I missed this step out in the last one. Lead nitrate, nitrates are all soluble. So this one here is going to be soluble. So this one here is going to be our aqueous. It's going to be our soluble one. Silver chloride, all chlorides are soluble except Ag for silver. So this one will form our solid precipitate. I should have done this in the reaction before. Copper hydroxide, all insoluble except sodium, potassium, ammonium. So that's not an exception. So up here, this one would have, this one here would have formed the solid. Sodium sulfate, all sulfates it's soluble except barium, strontium, and lead. So sodium isn't one of those exceptions. So this one here would have been our aqueous. The things we were reacting were both aqueous. If we were doing it in the lab, we would see they're both dissolved in water, so we'd know they're aqueous. But here, sulfates are all soluble except those ones, so copper's not an exception, so that would be aqueous. Sodium hydroxide are all insoluble except sodium, so sodium is the exception, so it's soluble and aqueous. So what I should have done to finish off this one above was put these subscripts in to show which ones were dissolved, i.e. aqueous, and which ones were solid. So now, back to this equation. Lead, symbol of lead is Pb, has a 2+ charge, just get that from the cheat sheet this year. Chloride, element number 17287, wants to gain 1 electron to get a full outer shell, forms a negatively charged ion. A minus and a 2+ don't balance out. We would need two, I think I picked the rubber there by mistake. We would need 2 chlorides to balance out the sodium, so there'd be 2 minuses, 2 pluses, that would be balanced. Plus silver, which is Ag, and it forms a 1+. Again, just from the cheat sheet you can get that, although it's written up here in this sheet as well to remind you. And nitrate, one of the polyatomic ions, again, that's up there above, NO3-, a plus and a minus balance, so that's all good. Back to our lead, 2+, our nitrate, NO3-, 2+ and a minus don't balance. Now, because this is a polyatomic ion, we've got to put brackets around all of it. It stays as this nicely held little bunch. It doesn't sort of change its little structure of polyatomic ion. So only got a minus, that's a 2+. We need 2 minuses to balance that out. So we put a 2 there. And then silver, Ag, it's got a 1+ chloride ion. Remember, we call it the chloride ion rather than chlorine, because when they lose an electron and form an ion, we change their name to ide. 1+ and 1- balance, so we don't need to do anything. There, that one is a solid. That one there is aqueous. We worked that out before. The nitrates are all soluble, so this here would be aqueous. Lead chloride, all soluble. Oh, this was a bad example to pick in a sense, because in a sense, lead chloride would be insoluble. Now, it is actually slightly soluble. We're not going to worry about the exact definition of how soluble or not soluble at this level. So strictly speaking, though, the lead chloride though would be a solid. So that would be more like adding a solid to a solution. It would still react to form that silver chloride. So it probably wasn't the best example to pick there, picking something that was insoluble to start with, but it still shows that whole process. So what we've done there, we know about the solubility rules of how we work things out. We've learned about how we work out a word equation, and then we've learned how we turn a word equation into a chemical equation. What we haven't done yet is balance those equations. We'll do that in the next slide. And then if you think back to our success criteria, it didn't actually say write full equations, it said write ionic equations. So we'll talk specifically about what an ionic equation is as well in the next slide. Okay, so in general, when you need to balance an equation, we generally find it best to follow this order. Do the metal atoms, do the non-metal atoms, other than hydrogen and oxygen, then do hydrogen, and then do oxygen. This sort of system will generally hold you up. You might have to go through it a couple of times to get there, but the process will work. So, what do? We start off with the metal. So let's start with copper. We have one copper here, and that's the only copper on this side, one copper here, one copper each side. So for starters, copper is fine. We don't need to do anything else to copper, one each side. Then we'll go to the other metal, sodium, one here, but Na2, so there's 2 sodium here. So that's not balanced. There's 2 sodium this side, 1 sodium this side. Got to have the same number of each atom on each side of the arrow. So the only thing you're allowed to do when you balance an equation is put big numbers in front of things. So we can put a 2 here. So now we have 2 sodium on this side now, and we have 2 sodium on this side. So sodium is balanced. Next we'll go to the non-metals. So we have got sulfur. We have got 1 sulfur on this side, 1 sulfur on this side. So the sulfur is balanced. That's all good. Then we'll go to hydrogen. We've now got 2 hydrogen on this side because there's 2 NOAHs. So that would be 2 hydrogen. And if we come over this side, we've got 2 of these hydroxides. So we've got 2 hydrogen. So the hydrogen's balanced. That's all good. And then finally, we'll do the oxygen. We've got 4 oxygen here. And we've got 1 there. So that's 5. Oh, sorry, we've got 2 here because there's 2 of those. 6. We've got 2 oxygens there because there's 2 of everything in the brackets. And we've got 4 here, so we've got 6. So that's it. That's all we needed to do to balance that equation. Let's come down to the bottom one. Start with the lead. 1 lead on this side, 1 lead on this side. That's balanced. Then let's go to silver. 1 silver here, 1 silver here. That's balanced. Then let's go to chlorine. 2 chlorine here, only 1 chlorine here. So we need an extra chlorine on this side. So we put a 2. Remember, we can only put big numbers in front. So now we have 2 there. But you can see we've stuffed up the silver. So we need to go back to silver. It's 2 silver on this side. There's only 1 on this side. So we need to put a 2 here to balance out the silver. So now we've got 1 lead on each side, 2 silver on each side, 2 chlorine that side, 2 chlorine that side. Then we do the nitrogen. We have 2 nitrogen, just things changing, 2 nitrogens there because there's 2 silver nitrates. So each silver nitrate only has 1 nitrogen, but there's 2 of them. And we have 2 here because there's 2 of everything in the brackets. So the nitrogen is good. Then we can do the oxygen where we've got 3, but we've got 2 of these. So we would have 6. And over here we have 2 3s. We would have 6 as well. So that would be balanced. So that gives us our balanced equations. If you feel you need some more practice for that, I did put this at the end of the notes for the activity, the practical activity that we've either done in class for some of you or others will do in class. So I'll just tell you where, if you feel you need more practice balancing equations, go to, just a Google search is probably easiest for PhET. And they have a whole simulation which is quite good, which is called balancing chemical equations. And it gives you lots of practice, it gives you different ways to look at it, and it will just help build your skills up in balancing chemical equations. Now, the one thing we haven't done here is done what's called an ionic equation. And an ionic equation is almost a shorthand simple equation. And in an ionic equation, we only worry about things that have changed. So, if we take this equation here, we can see that on this side of the reaction, the copper is aqueous, and on this side of the equation, the copper has gone into a solid. So the copper has changed. So that means if we were doing an ionic equation, we would put the, I'm on highlighter, not pen. We would put the copper into our ionic equation. If we then look at the sulfate ion, we can see the sulfate here is aqueous, and over this side, the sulfate is still aqueous. So sulfate hasn't really changed in this reaction. It's gone from aqueous sulfate to aqueous sulfate. Hasn't changed. So we're not so interested in the copper, in the sulfate, so we're going to leave that out of our equation. So we've just got aqueous copper ions, and they're reacting with sodium hydroxide. You can see, hopefully here, the sodium is aqueous on this side, and the sodium is still aqueous on this side. So it hasn't really changed. It's what we call a spectator ion. It's not really changing. Whereas the hydroxide here is aqueous, and then here it is solid, so it has changed. So that's important. That's something that is changing, so it's important. So wrong one again. So we put the hydroxide into our ionic equation. And then when we get to this side, the copper and the hydroxide are the ones that are changing from aqueous to solid. So they go into our ionic equation. But the sodium and the sulfate, they didn't change. They were aqueous on this side, they're aqueous on this side. They were what we call a spectator, if you like, in this reaction, so that we leave them out of our ionic equation. And we've still got to just check the balance here. So obviously, and it's in that one above, we need 2 of those hydroxides to balance out the copper, because that's only got a minus, this has got a 2 plus. We need that to balance out. So that is the ionic equation for the reaction between copper sulfate and sodium hydroxide. It's just a shorthand way of doing it. But you really normally need to write out the full equation to get to the shorthand way. Okay, now let's do the same thing with the equation below. I know I've got that mistake, but let's, for the sake of this argument, let's assume that lead chloride is aqueous. It's not very soluble, lead aqueous. It sort of falls in that gap in the middle. But just for the sake of this activity, we'll just assume that the question is right and it is aqueous. And it would dissolve a little bit, but only slightly. As I said, it's probably a bad example to pick, but it does highlight the fact that things sometimes are just a little bit soluble. Generally, we say things soluble or insoluble, but there is sort of shades of grey in the middle. So, looking at this one, we hopefully can see, we'll try and do this one a bit quicker. We can see that the lead here is aqueous, and over here the lead is aqueous. So it's not changing. Let's shade that out. It's a spectator ion. It's not doing anything. The chloride here is aqueous, and over here it's solid, so it has changed. So we do need to use that. We won't cover that up. The silver is aqueous here, and over here it's solid. So that one needs to be included. The nitrate is aqueous here, and it's aqueous here, so it's a spectator ion, so that we can sort of ignore that. Now, it doesn't really matter. Generally, we write the metal and then the non-metal, but we'll do it here. Now, we don't write Cl2 here, because what this really represents is the fact that we have, oops, wrong thing again. It's not Cl2 as in chlorine gas. This is a lead ion with 2 chloride ions. So what that really represents is a chloride ion, and it's aqueous there. And then it's reacting with a silver ion that's aqueous here. We won't worry about how much, we'll balance it at the end. Then the lead nitrate doesn't change much. They're still all spectator ions, but that goes to form silver chloride. That's got a plus, that's got a minus, plus and a minus balance out, so we don't need to do anything else there to balance them, and that's a solid. So that would be our ionic equation for that reaction. So, there's a fair bit there, I know, and if you've done this over the last couple of years, it's probably not hitting you all at once. But if you haven't seen this sort of stuff, you know, it is good practice and good skills. A year 11 student should be able to write and balance chemical equations. Understanding precipitation reactions and things, whether things will dissolve or not dissolve by using the solubility rules that were on the previous slide, is also one of the things that's in the year 11 chemistry course. So hopefully all that makes sense. As I said, go and play with that PhET balancing of chemical equations simulation if you think you need some more practice. Otherwise, that is the last flipped lesson for this topic on chemical reactions. We have now covered moles, we've covered concentration units, we have covered energy in chemical reactions, and exothermic and endothermic reactions, and we also covered dissociation things and hydration in that as well, and we've covered precipitation reactions and writing and balancing chemical equations and writing ionic equations. They are the key things that we needed to learn this term in chemistry. Cheers.